So now we will consider a similar but a different type of test. So think about this the same. Think about this now. Like what the regression model is the same. Actually, X includes X1 and X2, and X2 is endogenous, X1 is exogenous. So up to this point, exactly the same. By the way, it is from Bruce Hansen, Professor Hansen's lecture note on endogeneity test or subset over identification test. So there are many different names. I don't know what is what. But the idea, I'm just teaching you the idea. So there are some of the regressors are endogenous, and now we also classify the instrument excluded instruments in two two cases, two types. ZA is certainly valid instruments. So we know that there is no doubt that this ZA is endogenous. It is always exogenous. It's good. But the problem is ZB. ZB is uncertain. Like it may be endogenous, it may be valid. So that's what we would like to test. So so this is a general framework. So let's think about the details, like how we classify and what kind of setups can be analyzed in this framework. First is exogenated test. So X is composed of X1 and X2. As usual, X1 is exogenous. X1 is certainly exogenous, but X2 is uncertain. X2 may be endogenous or may be exogenous. I don't know. And Z2 is instrument. Now, we assume that Z2 is valid, certainly valid. So instruments are good. But what we do not know is whether a regressor is a vector of regressors. Some regressors are endogenous or not. If they are not endogenous, we do not need to use the instruments, right? If they are not endogenous, OLS is the best. But if they are endogenous, then the instruments are needed. So we have to decide what we have to do. This is example 1. So we are testing whether some regressors are endogenous or not. Example 2. Now, suppose that all of X is certainly endogenous. So some of X are endogenous. We don't have any question about that. So endogeneity is clear. But our question is, which instrument is valid? So some instruments may not be valid, some instruments may be. So also classify the instruments into two cases. You have to have certainly valid instruments, and we are testing these uncertain instruments. We can test these ZB. So the null hypothesis can be stated in this way. We are testing whether ZB is exogenous or not. And regardless of the null hypothesis, always we assume that ZA is exogenous. So in the earlier model, in example 1, ZA includes X1 and Z2. But now ZB is something different. And here ZB is simply just some of the instruments. And as you may have expected, we must be able to identify beta without ZB. So without using the null hypothesis, we should be able to identify beta only using those surely valid instruments. That is a requirement for this hypothesis testing. Otherwise, so that means you have over-identification and extra identification power, and this extra is utilized to test some instruments. So without the extra like ZB, you should be able to identify. So the dimension goes like this. The dimension of certain instruments must be at least equal to the dimension of the regressors, the parameter beta, right? Intuition is clear. And then how can we do this? We can think about wild test in this case. I'm just showing you the most widely used test, but you may try different types of tests in the same setup. Let's think about wild test here. And this part is based on textbook by Green. Green textbook considered is the best, has the best chapter about this setup. So I'm using his description, his explanation. So now let's think about beta U unrestricted estimator. Unrestricted estimator uses the certainly valid instruments only. So only use ZA, and then from here you can identify beta. Then you can identify epsilon. Then you can calculate this. So epsilon can be calculated, and of course ZB is in your data. So you observe ZB, and using ZA you identify epsilon. Then just calculate what is the covariance between them. The covariance can be calculated this way. Multiply them and take expectation is replaced by sample average, and now you may expand this to this. Then the what you need to do here is you have to derive its limiting distribution. So its limiting distribution can be driven like can be derived. It's not difficult, but it's not clean. So I will not show you how to do this, but what you need to do here is just you need the variance. So if you can calculate the variance, then your test statistic wild test will converge to chi-square now MB. This is the dimension of ZB, the uncertain instruments. So you are testing MB number of instruments. That is the degrees of freedom in this case. So this is how you can use wild test in this case. And I will show you the same, in the same setup, we may use Sargan and Hansen's J-test. This is J-test, yes. And Hansen, this Hansen is different Hansen. So the lecture note, author of the lecture note is Bruce Hansen at Wisconsin. And this Hansen is Lars Hansen at Chicago, who won the Nobel Prize several years ago. And he invented GMM method. So that's why his name is included in here. So now this part is based on Hansen's lecture note, Bruce Hansen's lecture note. And think about the criterion function as before. And now what you are doing here is simply you may think about two different moment functions. One is you can think about the moment functions without using the uncertain instruments. So only use the certain instruments and they are used as the moment function. That's the unrestricted model. But in the restricted model, you include all the instruments. Of course, you include surely valid instruments and also include uncertain instruments. And so this will make more moment functions and will give you the restricted, the criterion function for the restricted model. So using the unrestricted model's criterion function, you can minimize the criterion function. And similarly, if you use additional instruments like this, define the criterion function in the same way, following the GMM method, and then minimize the GMM criterion function. And then, as you know, unrestricted model will have smaller minimum because it's unrestricted. You are using fewer restrictions, so therefore our test statistic is defined based on this way. And what is interesting here is that ah you so this is following chi-square. So there is no standardization needed. By the way, let me clarify this. So let me clarify. So the reason why n is multiplied here is because so if it depends on whether omega hat includes n or not. So like remember, depending on the definition of asymptotic variance, the variance must be divided by n, right? So the asymptotic variance is approximately the variance of estimation error divided by square root of n. So we have to handle this square root of n, and that is multiplied here explicitly, assuming that omega hat does not control that, does not control for the square root n, but here, in here, I am implicitly assuming that the square root n is handled by the variance. So it's my notation mistake. Uh, so, but if you do the algebra, then n should be and maybe multiplied or not, depending on how you define the variance and the weighting function. So both are correct, but just it's inconsistency within my notation. So okay, this is anyhow all this is converging to chi-square, and this is the end of hypothesis testing chapter. And I will post homework number 5, right? And we'll continue to the next one soon. See you later.